Hello and welcome to another Toddcast. We're continuing on with alkene reactivity and building an arsenal of different reactions that we use for synthetic purposes, synthesizing one molecule from another. So far, Toddcast 40 through 44 have all dealt with this concept of alkene chemistry. And we've seen a pattern where a lot of times, if it's syn addition, they'll add to the same side at the same time. If it's anti-addition, one will go on, form this three-membered coordinated ring system and be attacked from the opposite side. So anti, if they go on one at a time, one will go on one side, make that side crowded, and the other one go on the opposite side. So 44 really was kind of the pinnacle. That was that uh, sort of brought everything together mechanistically. And so 44, I mean, just if you're a baseball fan, historically, it's a very famous number for a lot of people. So it's a very good number. So 44 is a good thing. Hopefully this one will follow in suit. So much for numerology. Um, we're going to kind of complete one spider chart and then go into another one. So for this, want to talk about hydrohalogenation. So it's a slight spinoff of what we did with just HBr. So when it's just HBr, the H went where H was. So again, the right one has an H, so H is less crowded. So the first thing on will go to the side. And so we have this unique situation where it is a case where first thing on chooses a better seat, but if it's HBr without peroxide, then H is the first thing on. But when we use peroxide, and actually the peroxide picks up the H and leaves the Br as the species, it's going to be first to go on. So the Br chooses the better seat. Ultimately, the Br, the more bulkier group, is going less substituted. So this ends up being a anti-Markovnikov addition. And so one of the things that hopefully when you look at your spider chart, you start seeing the big picture, you'll notice whenever we use a peroxide, be it as a solvent, a reactant, a chaser at a second step to uh, kick off a boron, whatever we end up using it for, peroxide usually leads to anti-Markovnikov. It's just one of those things to just clue into in your memory. So BR goes on first, attacks less substituted carbon. The H ends up on the second one. This is done by a radical intermediate. So just to note what a radical is. So bromine, we normally, as an ion, think of it as Br negative. When you don't have a full octet, you just have 7, it's known as a radical. So this is bromine radical. It has no charge, and it is highly unstable. You do not want 7 electrons. It's going to find that 7th. So it does so by interacting with the pi bond. Okay, there we go. So this electron will interact with an electron from the pi bond. So we'll go through the mechanisms as we go, but just note, this is anti-Markovnikov. Because it's going on one at a time, I would think it's anti, but it ends up, it's a weird enough mechanism where you don't form that three-membered ring, and so you can actually get random stereo selectivity. So this is a case of no stereoselectivity. And in this case, although we have a Carl center here, we have none here. So this one could go front or back. So no stereoselectivity for this one. The mechanism. Okay, so this is our first step into free radical chemistry. We will spend more time in future podcasts covering it. But for now, peroxides, highly unstable. That's why you keep them in a brown bottle. Sunlight added in, you can break that very weak oxygen-oxygen bond, and you end up, and I've only drawn the one single electron that matters in the free radical reactivity. But just so you know, there is a consideration of other electrons. So each of the O's have 2 lone pairs in addition, but still you have that single highly reactive electron. It is going to interact. So H does react first, but instead of reacting with the alkene, as mentioned, it reacts with this free radical. A single-headed arrow represents one electron. So normally, if you see an arrow that's double-headed, that's two electrons. You see an arrow that's single-headed, that's one electron. So these are one electron movements. Okay, so just like cations, anions, free radicals the same way, if you have one, you have to keep track of it. So if I have one as a reactant and then none here, then I must have none and one. So the bromine ends up free radical. And again, want to emphasize that there are other lone pairs. Okay, that bromine free radical is now going to react with alkene. Alkene is the most reactive species there is outside of the peroxide. So the alkene can split its pi electrons to a free radical here. This free radical can go out and meet with the bromide free radical. And I should be careful. It's not bromide, it's bromine. So it will attack, and you have a new bond to bromine. Well, you have a free radical. This free radical can do what the peroxide did, and that is pick up an H. So to make this reaction go, you have to put the right quantities in. If you put too much peroxide, then there won't be enough free HBr around to react with alkene. So this is just an initiator, just gets it going. So we put a very small amount in the beginning, and then we hope that the stoichiometric relationship between HBr and the alkene, the one-to-one relationship, means that once you make this free radical, it'll react with the HBr, which creates Br, which will react with an alkene, which in turn reacts with an HBr, and so forth. So it propagates itself. So you use it up to start it, and then you regenerate the Br free radical to do it again and again and again. So this becomes this, which is the reactant in the cascade. So ultimately then this Br is free to react with another alkene. So the system feeds on itself until it runs out of reactant. But the key thing, it goes on with Anton-Markovnikov stereochemistry. And because this is free to rotate these groups here, the stereochemistry is not as predictable. So this group, because it's not sp2, it's not going to be planar, it's going to be, tetrahedral is the best description, but there's only one electron, so it may not have the full 109.5 angle because it's not the same amount of repulsion, but it's still going to be something like that. And so these groups will line up in a way to minimize steric hindrance with this. So there's always going to be some stereo preference if you're next to a stereo center, but it's not as obvious pronounced, and we generally don't pay too much attention to it. Spider chart is about to be complete. We have one more to add in here, HBr. Note peroxide. So I want to make just an overview of what's going on in these reactions. Anytime you see peroxide here, it's anti-mark. Here, anti-mark. And then the other time we use a peroxy acid, there's no anti-mark compound to speak of because you're getting two of the same group on there. So that one doesn't quite apply. But peroxide should give you a hint that it's anti-Markovnikov. And then ring formation, ring formation, ring formation, ring formation for the Br, the Cl2 is the Br2 substitute. So ring formation, ring formation, ring formation, you get the two stereoisomers. So if you're getting anti, you're probably getting it through a ring-formed intermediate. Okay, couple reactions that are not on here that you might want to make note of. This one, there is also the ability to use HGOAC2. And then that's step one, you have to follow that with, that's step one, I should say. Step two, I'm spacing this poorly, I apologize. It's plus number one, and then number two, your NaBH4 in the appropriate solvent. I ran out of room, so I'm just going to leave it as that. So that's an alternative for adding the OH where you don't get rearrangement. And then you might want to note that this could also be Br2 and CCl4. If that's the case, you'll get Brs in place of the Cls. In this one, you could also potentially use ETOH, MEOH, some alcohol, in which case this OH would become the OET or the OME. So just have flexibility in what you do. Know how these are working. This one, the important thing of the hydroboration is that if you mix it 1-to-1 ratio, then you will get a lot more Markovnikov impurity. If you mix it in a 2-alkene to 1, then you get less Markovnikov impurity. And then if you mix it 3-to-1, that's optimal and you minimize your Markovnikov impurity. Okay, so spider chart, it is worth your time to screenshot this without my writing. Fill it in yourself, because when you fill it in yourself, it'll be better. And know the nuances. Write yourself lots and lots of notes on this one. You're going to have to know every single feature of these to make it useful in synthesis and mechanisms. Okay. Now for the second spider chart, the smaller one with only 4 reactions. We have one on there so far. The mercury acetate is on that one. I put it on the one we just did as an afterthought, but it's going to be on the other one because it's important. Couple other reactions to consider. KMnO4, rich in O, it's an oxidizing agent. You end up adding O. Note that they're both on the same side. And so a real subtle hint is when you use a metal, you generally get syn addition, mercury being the exception, so I don't want to say it's always true. But H2 with palladium, H2 with platinum, MnO4, you typically are going to get syn addition. Both OHs add simultaneously, hence they are syn. And then the MnO eventually gets released off as goes from MnO4 to MnO2. Radioselectivity, adding OHs to each side, so irrelevant. And stereoselectivity, absolutely, syn addition. OSO4 is an alternative. KMnO4 is awfully toxic. Osmium tetroxide, not quite as toxic and a lot cleaner to work with, a lot easier to clean up the mess afterwards. Note you get the same reaction, just there's a cost differential. But both these reactions are perfectly fine. We do our chemistry on paper, so either one of these work. Not a big cleanup. If you write the wrong thing, you just erase it. In lab, a lot of cleanup issues with this. So the mechanism, and I want to qualify this, the mechanism here is more of what they call a scheme than a mechanism. So it shows the same steps, but mechanisms take the time to look at the kinetics and make sure the sequence is correct, the orientation, the alignment of all the atoms is correct. A scheme is the most probable mechanism, but it hasn't been completely sorted out. So these O's are going to go on these respective carbons, but the exact sequence of how this happens is open to debate. So I'm just going to say this is a scheme. These are all moving around. So you now have delivered 2 O's to the same side. The Mn very much wants to release and be on itself. So instead of being MnO4, you're going to see it just come off as MnO2, and those H's are going to go there. These are going to go undergo hydrolysis. Water is going to attack, in this case OH, and bring it there, basic mechanism. And this is now going to see something similar where you can protonate there, and an OH is going to attack and do the same thing as before. So protonate to make it neutral, and then the OH is going to come in, do the similar thing, attack there, come out, and the water is going to take care of it. So your Mn water gets dehydrated down to MnO2 when it loses those. So for this one, just for what it's worth, you can deprotonate here, that's going to kick in, and then you'll end up also doing the dehydration to get rid of it. But irrelevant, we're not worried about the MnO2. We're worried about this, the syn addition. And again, I'm going from bottom side, we could easily go from top side. Osmotic tetroxide, same story. You're still going through the same intermediate, same compounds. So we're going to ignore, I'm going to very much not care about the manganese result or the osmotic result. So you'll notice if you really took a fine tooth comb to this, that waters are magically appearing and disappearing. We're not going to worry about what happens there. We're only going to worry about what happens to the organic molecule, organic chemistry. Spider chart. So the oxymercuration reaction had here from before. I just actually want to add in the fact that this must be done in an ether of some sort. Water kills that reagent. So we have permanganate. Must be done cold. If you do it hot, this oxidizing agent can actually start turning these into different compounds. So key thing done under cold conditions. And then OSO4 followed up by sulfite, sodium sulfite. So should call it sodium bisulfite, excuse me. And again, syn addition. One reaction to go. And this is a cool one that we will use a lot in synthesis called ozonolysis. Reacting with ozone. Ozone has a grand total of 3 O's. Those O's can be located here, here, and here. So we're just relocating oxygens in ozone. So note that this has no oxygens. Now you've had 2. The sulfur has no oxygen. Now it has 1. All your O's are accounted for. So O3 adds first to the pi bond before inserting an O into the sigma bond. It is really bizarre how this works. And then the dimethyl sulfide comes in and becomes dimethyl sulfoxide by picking up that third unloved, unwanted oxygen. So we'll look at the mechanism. So regioselectivity, not involved at all. Other ones we can say it's irrelevant. This one just isn't involved because it's just, you're not getting a stereocenter, you're turning it into a ketone. Stereoselectivity, not getting regioselectivity, stereoselectivity, you're getting an O on each side and no stereo because sp2. So completely irrelevant, but it's the first of reactions where we can break a double bond, a carbon-carbon double bond. And so you need to hang on to that thought that, let's say on an exam, you're asked, how would you convert that into and then they try to get tricky and draw this like that. You draw it split away. You would simply say, this one splits a pi bond. So I've got 1, 2 carbons, 1, 2, 2. And on the other side just comes out, I got the 1 carbon. So it's when you see a pi bond broken, when a ring's opened or a molecule's broken into fragments, like the example up here, you know ozonolysis probably is the culprit. So useful shortcut, just put a squiggly line through that bond, add a couple of O's, so stretch it out, and put 2 O's on. Pretty straightforward. So fairly easy to do. Hopefully one of the things you recognize. O3. Mechanistically, this one is a mechanism, not a scheme. We've actually studied it well enough to know that ozone is this resonance stabilized O minus O plus. This can kick in, that goes out there. This becomes O minus, that's the O plus. But the minuses are going to interact. So you basically have the 1 minus come and attack here, the less crowded side. Pi bond breaks and attacks at O, which sends its electrons over to here and makes this now no charges. So overall, this is uncharged. It's known as this Zuid ion. It has 2 charged sites that cancel one another out. Overall neutral, but it's charged. Now it is completely uncharged. I'm going to emphasize the 2 O's here as important because those are the ones that are involved in the oxidation of that molecule. This is really weird what's happening. So let's go ahead and draw those arrows into bonds. So let's start with this bond right here, apparently is leaving. So I'm going to erase this bond and turn it into a bond from that O to that carbon. And then this bond is now going to that O as well. And so, I connected that wrong. That's going there. That's what that arrow did. And then this bond up here is now going to disappear and turn into a bond from that carbon there to that O there. Looks really confusing. So let me erase this and draw the picture. Notice the atoms are in the exact same spot. This O, same O, this O, same O, this O, same O. This bond went from here, from this carbon to this O. So that bond there has become this bond here, the one in back. This bond here has become this bond here. So it's from this blue O to that carbon. This is from this carbon here to that middle O. So again, no atoms have changed positions. I simply have turned this bond here, let me make it yellow, has become this bond right here. And let me make the other bond green. That green bond has become that green bond. So bonds just simply moved around. Atoms are in the same spot. I'm going to redraw this because now this O is isolated. That actually equals this molecule. It's a peroxide, so not terribly stable, but this intermediate rearranges to this intermediate. And now it's a matter of sulfur coming and doing its magic. So sulfur is going to take the unloved O from here. Reality is you could choose either side, but I'm going to choose this one. Sulfur is going to somehow get this O. So let's just look at how it's going to work out. This lone pair is going to attack the O, which pushes those bonds to there, that bond there, and brings that back over. So again, without any atoms moving. So I don't know if you can see this, but I literally took this structure, these two, cut it and paste them over there. I left everything, the O's in the exact same spot, sulfur in the exact same spot, and not exactly, sulfur is drawn below it, but the ring system, let's again figure out what bonds go where. So this green bond here becomes that pi bond there. This bond here becomes that pi bond there. And this lone pair becomes one of the pi bonds to O. And this, what color have I not used? They're not used yellow. This bond here becomes the second bond. Hopefully the color coordination helps if you can track it that way, but it's a reaction that's followable, but relatively complicated. This one took a lot of work over the years for people to figure out exactly how the mechanism works. Okay, spider chart time. Can I complete our spider chart by having ozonolysis in the shortcut, cleave, and add some O's. We do that, we now have a 1, 2, 3, 4, 5, 6 membered ring, the methyl hanging off. This O had an H, so that's this one right here. So let me number it. 1, 2, 3, 4, 5, 6. So I have to have a carbonyl on 1 and 5. I have number 6, CH3 dangling off of 5. 1 connected 2 to 3 to 4. So numbering helps a bunch. You really should number. Okay, gonna get rid of my drawing and say we are done for spider charts. 12 reactions that have spin-offs. And if you really looked at it carefully, you could probably make an argument that there's about 40 to 50 reactions by making very subtle changes, like adding, instead of DMS, we'll add a peroxide. Peroxide will turn this into an acid instead of an aldehyde. Little nuance changes like that. Instead of using water in this, we're going to use, let's say, ethanol or methanol and get an OCH3 instead, or OET. So there's variations on it. but there's 12 fundamental core reactions that if you understand those well and know how things twist and turn, you can figure anything out in alkene reaction chemistry. So we got through the tough part. This finishes all our spider charts. So thank you once again for joining in yet another Toddcast. Hopefully this sort of tied everything together, and I will see you at the next Toddcast. Bye.